connect up the high redshift universe with the low redshift universe, and also kind of talk about the intersection of dwarf galaxies and globular clusters. So that's what I mean by the faint frontier of galaxy formation here. This is work I've done with a bunch of people in this room, or it's been inspired by a lot of people in this room, or who will be in this room, or who have been in this room. This room has been very important, clearly. And you can find this in a couple of papers that are on the archive or that may at some point appear on the archive. I'd like to especially point out my grad student Alex Fitz, who's done a lot of important simulation work that I won't have too much of a chance to talk about, but I think has inspired a lot of my thinking on this. So we heard a lot of really good introduction on this kind of topic earlier today from Richard and Steve and various others. I think the point basically being that in the current cosmological paradigm, reionization is crucial for understanding the universe around us, because it's what suppresses galaxy formation in the lowest mass dark matter halos. Otherwise, you end up with missing satellites problem and various other issues, overproduction of stellar mass in general. But on the other hand, we also need the low mass galaxies, as we heard from Steve, to kind of drive cosmic reionization. So there's this kind of chicken and egg, or you know, are dwarf galaxies the drivers of reionization, or its victims, or both? So we'd like to be able to study them and try to figure this out. The problem is that low mass galaxies are inherently hard to study. They turn out to be low luminosity also. They're far away. That makes it even worse, right? So what I'm going to talk about is using not direct observations in the reionization era, but the stellar fossil record of the reionization era stars in the local universe today. Okay, so like the famous quote goes, reionization is the cause of and solution to all dwarf galaxy problems. So just to put us all on the same page, here are a bunch of dwarf galaxies. Yes, they actually exist. So some of them are, you know, somewhat spectacular, LMC. This is all on the same physical scale here now. Fornax, already can tell, is a dwarf galaxy. Pictoris 1 is startlingly unimpressive, I'd say, on this scale, but there's a lot of interesting physics that we can do by looking at these things. And I'd just again like to point out that the difference in stellar mass from the LMC down to Pictoris 1 is about 6 orders of magnitude. So when we talk about dwarf galaxies, we're talking about a really broad range of systems. Okay, so here again is Fornax. This is the brightest classical dwarf spheroidal in the Milky Way. Has a stellar mass of 5 times 10 to the 7 solar masses or so. And you can see there's a lot of information here. We can actually do galaxy formation on a star-by-star basis, because we can do resolved color magnitude diagrams of the stars in this galaxy. Another point I'd like to make is just the size of this thing on the sky. This is the size of the Hubble Ultra Deep Field compared to the size of Fornax. Okay, so everything we know about the faintest galaxies in the universe is from a field this size. We're actually, you know, don't even cover a very significant fraction of this galaxy with that size field. And Andrew Grouse will be talking about that later this week, what some of the implications there are. So what do we know about reionization era star formation from dwarf galaxies? Well, every galaxy that we've studied in sufficient depth, that is, we've reached the oldest maiden sequence turnoff of observations, we've seen star formation at the earliest epochs. That is, there's no galaxy that I know of in the universe that did not have ancient stars based on a resolved color magnitude diagram. Okay? And furthermore, the lowest mass systems seem to have the highest percentage of their stars formed early for the dwarf galaxies around us. And that's kind of encapsulated by this plot from Dan Weiss's work. What it shows you is the cumulative fraction of stars formed as a function of look-back time. So the present day here is 0 in each plot. You can also see on the upper axis it has redshift, if you prefer that kind of unit. So these are low-mass systems, below 10 to the 5 solar masses in stars. These are high-mass systems, on the dwarf galaxy game anyway, above 10 to the 7 solar masses in stars, right? Beasts of the cosmos, yes. And so what you can kind of see, if I just draw a very careful line here in Keynote at 80% of the stars formed, these lowest mass systems have formed 80% of their stars by redshift 4 or 5. These most massive ones have formed 80% of their stars, I don't know, only within the past couple of gig years. So it's really a differential effect as you go up in mass. Great. So with resolved stellar populations, then we can kind of try to put these galaxies into the context of the high redshift galaxies we heard a lot about before. So this is a high redshift galaxy luminosity function, data from Richard and Steve here, and I've just extrapolated below the HUDF limit. You can kind of see where the JWST deep limit might be, so an ultra deep field in JWST. And of course, we don't really have terrific information here so far. We now know from the frontier fields there are galaxies, but we would like to know more about what happens to the galaxy luminosity function. So what we can do is just take the resolved stars that we have around us and run the clock back and ask what those galaxies looked like in the reionization era. So let me do that. We take the LMC, the most massive galaxy in the Milky Way, besides the Milky Way, of course, which has a stellar mass of a few times 10 to the 9. And if you run the clock back and ask what the UV luminosity, the intrinsic UV luminosity that would be in the reionization era, it would actually be fainter than what you can study with the Hubble with the Hubble deep field. Okay, so when you look in the UDF, the galaxies that you're seeing are all brighter than the LMC probably today. So they're progenitors of things like Milky Way or probably even more massive systems. Everything in the UDF. If we take a step down by a factor of 100 in luminosity, remember these are the brightest dwarf spheroidals around the Milky Way, a few times 10 to the 7. They actually sit down here at around minus 12 or so. Okay, so much, much fainter than the UDF limit. And if we go down to the faintest classical satellites, so something like Draco or Leo T, they're even further down here still. So at maybe minus 8, this is 9 magnitudes fainter than the UDF limit. Okay, and these are galaxies we can study with thousands of resolved stars today. And just in case you think about this more easily in terms of star formation rates, we're talking about getting down to star formation rate of well below 1,000th of the solar mass per year to get these kind of UV luminosities. These are really hard to study, even locally potentially. But again, the point that's important and why we actually care about this, as we heard earlier, is that galaxies kind of in this range here, we think are required to power or maintain cosmic reionization. That is, galaxies like the Fornax dwarf spheroidal that I showed earlier seem to be important for providing those UV photons to reionize the universe. We can push this even fainter to ultra-faint galaxies. Remember on that previous plot, that was only down to the classical satellites. These are now those really ultra-faint ones. These images, I've blown them up a little bit. They're actually color enhanced, so you can see some of the stars here. If you don't do that, they look really boring because it's just background and foreground, background galaxies, foreground stars. But the point here, again, that I'd like to make is that the star formation histories of these local group ultra-faint galaxies tell us that they were forming stars in the reionization era. They weren't forming many stars, they are ultra-faint, right? But it requires the existence of these super, hyper nano galaxies, whatever you want to call them, at very high redshift. So UV magnitudes of -3 or something like that. Now that's 14 magnitudes fainter than the UDF limit. And this is just a simple consequence of the low luminosities coupled with the ancient populations in these ultra-faint. So if you do that, you're kind of talking about going down to 400,000 times fainter than the UDF limit. You can say there must be galaxies down there in the reionization era. So we heard from Steve that there's probably, this can't continue all the way down. That would way overproduce the stellar mass, so you can't have a steep luminosity function. But on the other hand, there's no sharp cutoff, I think, way down. I mean, there have to be galaxies forming stars in the early universe, otherwise you wouldn't have these ultra-faints around us today. Okay, let's go back to Fornax. So, beautiful galaxy. What are these weird things here? Well, they're globular clusters, of course. So Fornax has 5 globular clusters in it, actually. They're conveniently labeled on the sky, which is handy for those looking for globulars. So why do you care? Well, I didn't used to, but you know, the scales have fallen from my eyes, and now I see. And you know, globulars are really interesting for a number of reasons, and I'll try to convince you of some of them here. But in terms of the contribution to reionization, let's think about the Milky Way satellites. The Milky Way has kind of 12 dwarf spheroidal galaxies that are more massive than 10 to the 5 solar masses in stars today. Maybe a few hundred total galaxies if you correct for the sky. coverage that's been done. Most of them are very low mass, these ultrafaints. But we also know that in the Milky Way, there's 100 old globular clusters, basically consistent with reionization era stars, each of which has an average of 2 × 10⁵ solar masses in stars in it, okay? So there are way more globular clusters than there are classical dwarf galaxies, and their star formation is entirely ancient, basically. So if we're thinking about what's happening at early times with star formation, globular clusters are likely to be very important, and looking just at dwarf galaxies may not be the way to do things. One way to think about this is 20 to 25% of the oldest, most metal-poor stars in the Fornax dwarf galaxy reside in the globular cluster. Okay. So the old star formation in Fornax is really encapsulated by these globular clusters. And so I think this shows that ancient star formation in globulars may be comparable to or even exceed the star formation in dwarfs and the reionization. All right, another interesting thing about globular clusters, the mass of the globular cluster system. So if you take all the globular clusters in the Milky Way and you add up their mass and you compare it to the mass of something else about the Milky Way, you can compare it to the stellar mass, the dark matter halo mass, whatever mass you want. It's become clear that the mass of that globular cluster system does not trace stellar mass, it traces dark matter halo mass. So there's something interesting there. That's basically telling you that globular clusters are the only kind of star-forming tracers that I know of that actually trace dark matter halo mass linearly, which is a little bit weird. Is there a question? In what way do they trace the halo mass? Very good. I just whipped this plot together for Avishai. So here is a plot of the stellar mass of a galaxy versus the total mass of globular clusters. So you add up the number of globular clusters and multiply by the average mass of a globular cluster, for example. Right, so in terms of stellar mass, this has a characteristic bend here, just like the stellar mass-halo mass relation. You say, aha, just like the stellar mass-halo mass relation. Let me plot this as a function of the inferred halo mass. And you actually get a linear slope here, okay? And it looks like it starts to break at dwarf galaxies, but I think this is just a misestimation of dwarf galaxy masses. From basic counting arguments, we'd actually expect these dwarf galaxies also lie on this relation. So it seems pretty clear that actually all the way down to where you host one globular cluster, which would be somewhere around here, the globular cluster mass, the system mass of globular clusters traces dark matter halo mass, which I think is telling us something fundamental. Very recently, Mike Hudson also had a paper out that says this is also true for the sizes of globular cluster systems. They don't trace galaxy sizes, but they do trace dark matter halo sizes. And it's long been known that the radial profile of globular clusters, of old globular clusters, actually traces the stellar halo reasonably well, or looks like it's clustered like high sigma peaks in the density field at early times. So this is consistent, all of this, with globular clusters being a relic of star formation in dark matter halos at early times. Okay. So to me, the physical interpretation here, and this is not the only physical interpretation, is that at very early times, you're actually able to convert a fixed fraction of your baryons from into globular cluster stars, but that's not the case for any other kind of stars that we know of. The other interesting thing that's been a huge development in this field recently is the realization that essentially all massive globular clusters have what are referred to as multiple stellar populations. So they're not simple stellar populations, one just simple epoch of star formation. You look at them, you have a first generation of stars. It's chemically identical to the halo stars of the Milky Way. But there's also a second generation of stars that looks completely different. Okay, it's enriched in helium, sodium, nitrogen, aluminum, some other elements, and depleted in carbon and oxygen. So this is all evidence of high temperature hydrogen burning, maybe a few tens of millions of degrees. Okay, so maybe AGB stars are doing this, maybe fast rotating massive stars. But basically every model for multiple populations that I know of has to invoke birth masses that are much, much larger to account for the fraction of these second generation stars in these globular clusters. Okay? The point being that if you have 70% of the stars being these second generation stars that are this much enriched, and you know how many AGB stars can do the enriching, you need a lot more AGB stars than could ever be present if you just had the same amount of stars that were around today. So depending on assumptions, if you say that globular clusters, there are 100 of which around today, each of which has a few times 10 to the 5 solar masses in stars, and maybe they're 10 or 100 times more massive in the past, now we're really in business somewhere here, right? Maybe these globulars are very important for reionization. So the overall takeaway here, these old blue globular clusters, they are ancient, they are numerous, they trace dark matter halos, and they're potentially crucial for reionization. Okay, so let me just do a little simple modeling here. Let me just say that the old globular clusters are born in the reionization era, so something like over a gigayear period from Redshift 10 to 4. Okay? And let me assume that they're born with a log normal luminosity function. So we observe them today with a log normal luminosity function. That could be a product of evolution at the low mass end, or it could be a reflection of the initial birth mass. And if you do this and you just assume that they form in proportion to the halo mass above a fixed threshold, you can figure out what the lower mass limit for globular cluster formation has to be. And that turns out to be about 10 to the 9 solar masses in this kind of model, or a few times 10 to the 4 Kelvin, so a little above the atomic cooling limit. This is, again, consistent with the picture that these are all forming kind of dwarfy galaxy halos at early times. And you just trace this back to when they formed. If it has a log normal luminosity function today, it has a log normal UV luminosity function when it formed. And if the typical mass, again, is a few times 10 to the 5 solar masses in stars, the luminosity function looks exactly like this with a peak at minus 14.5 rest frame UV. Okay, so now what we can do is just start to build up on this. So we say that globulars are just constantly forming over this redshift period 10 to 4. So it'll form over a 5 megayear period and then just passively fade. So we can do this from stellar evolution models. So we can ask how all of the globular clusters start to build up together to form a luminosity function in the high redshift universe. So this is that initial 5 megayear population. After 50 megayears, goes like, it looks like this, all the way down to 1 gigayear. Okay, you're just starting to build up more and more because you're always producing new ones at this kind of population and fading down here and adding up on top of each other. So what you can see is that you're actually building up more power law profile with an exponential cutoff than this initially log normal luminosity function. You can do this fully analytically, actually. You actually can approximate the globular cluster luminosity function in the high redshift universe as a Schechter function with a slope that is completely set by the stellar physics. Okay, this is just how the UV luminosity falls off for a given population after the stars stop forming. And this cutoff here is just given by the most massive globular clusters you get in the universe. So now let's look at this compared to galaxy luminosity functions. So these are from Steve's compilation from last year's review article. Okay, redshift 10 in the darkest purple, redshift 4 in the lightest orange. Okay, so you can actually see that globular clusters in this kind of model are not in excess of the actual observed luminosity functions, which I take as a good prediction. Right? We shouldn't have seen more galaxy or globular clusters than there are actual sources in the universe. But it's actually an appreciable fraction here, you can see, especially near the UDF limit of minus 17. But remember, in this model, I took that the globulars are actually the same mass as they were born. Now we can say, let's assume that they were 10 times more massive or 100 times more massive at birth. That means you move things over by 2.5 or 5 magnitudes to the left. Okay, very quickly you start to overproduce the number of faint sources that are actually detected in the UDF already. So to me, this is, I think, pretty strong, or it makes it very difficult for me to see how you can reconcile these models of very massive globular cluster birth masses with actual observations in the UDF. So let me try to make that a little more concrete here. So, basically the point is that these old globular clusters have a stellar mass that's comparable to a Milky Way satellite, but they form their stars in 1,000th of the time. So they're a much more important contributor per unit time, or per unit object to the luminosity functions. So they may be both important and observable at high redshift. So in these models that I just kind of made here, you can basically ask how many galaxies should there be brighter than a given UV luminosity in the high redshift universe, depending on this value C, which is the birth mass to present day mass. Okay, so you can see that for the UDF, there maybe would be 20 galaxies that are actually just detections of globular clusters in the UDF, even if just they have the present day masses and nothing more. And we know there's something like 150 to 200 sources from redshift 6 to 10 in the UDF. That basically, again, gives you this limit that it's very hard to understand how globular clusters could have been a factor of 30 or 100 times more massive in the past. Why wouldn't we have seen many more of them in the high redshift universe already? Of course, JWST will go fainter. This is pretty exciting because then it says we should already see something like 80 of these in the in a kind of a similarly deep pointing with JWST. And again, you have to multiply these numbers by 2 because I've done this for 5 square arc minutes. JWST field of view is like 9.7 arc minutes. So maybe 100, and if you can get all the way up to 10, there might be something like 1,000 globular clusters that you could detect between redshifts of several to 10 just in a deep luminosity function, or deep pointing with JWST. And so again, just to give you some numbers, note that even if you just have the present day mass is the same as the birth mass, 5% of all globular clusters from our known luminosity functions, which we can actually do very easily in the local universe, 5% of those globular clusters will be detectable at some point by Hubble even. You know, we'll reach an intrinsic UV luminosity of -17. Now, there's this real issue that Steve touched on, and that is a problem here again, which is this issue of escape fraction, or how much of that light actually gets out. Of course, for globulars, basically we know as soon as the type 2 supernovae start to go off, they'll completely blow out the gas surrounding that forming globular. So slightly after they stop forming stars, I'd expect them to be UV bright. So they may not get caught at very perfectly at the peak with 100% escape fraction. They should have high escape fractions shortly after the peak when they won't have faded that much. So I'll skip this bit. Oop, maybe try to skip this bit. And so I think the takeaway points here are that all measured local group galaxies have ancient star formation, which tells you that there basically have to be UV bright galaxies, or well, bright is not the right word here. There have to be galaxies that are UV faint but exist all the way down to very faint magnitudes in the high redshift. Also, globular clusters are full of ancient stars, and their star formation correlates with dark matter halo mass, not the stellar mass at redshift 0, which I think is intriguing. You notice that I haven't actually given you a detailed model for globular cluster formation. I'm not that masochistic. I'm sure that would be wrong, but I think these correlations are intriguing and really merit further work on this. And the model where globular clusters form in high sigma peak in the density field, I think was maybe originally proposed here and work by Sandy and others, seems to work very well. And globular cluster UV luminosity function in this kind of model will extend with a fairly steep slope all the way down to a UV magnitude of -7 in the high redshift universe. And I think all of these considerations really lead me to the fact that it's very hard to believe that globular clusters had 100 times more mass in stars when they formed. And basically, there's no good model. And I think the people who do globular cluster formation models would also agree there's not a really good model for understanding these multiple stellar populations. So we need some more work on that. And I think I'll stop there. Thank you. Why? Well, so, I mean, it's not 100% obvious, but I think if it's true that globular clusters form with a luminosity function that's log normal, it speaks to me to some kind of Jeans mass. Okay, and the Jeans mass in low metallicity gas with a UV background would be around 10 to the 6 solar masses there. So I think that gives you this kind of characteristic mass of a few times 10 to the 5. So again, this is just in kind of, sorry? So you want to make them in a big halo, but you don't want to make them have all the gas flow directly to the center, because we know that they don't have huge amounts of dark matter. So I think that sort of some kind of combination of the models that sort of Peebles or Rosenblatt would have had with the compressive shocks models of Gunn et al. Would probably, or I think it's just Gunn, would probably work. So what you really need is an epoch where there's very low metallicity gas with lots of mergers that are driving compressive shocks. You don't want this to be happening the centers of dark matter halos. So after the reionization era, the merger rate for dwarf galaxies does drop substantially, and I think that picture at least loosely holds together. There's a paper by Mikola Trenti et al. That kind of fleshes this out a little bit more detail.
I mean, at this point, I don't know if there's also going to be discussion questions.
Right, so if you look at the region of the local group, it's completely normal in terms of its abundance for anything that is at least as common as a 2 sigma or 2.5 sigma peak or lower in the density field in the reionization era. So I think that if you go to the LMC kind of mass, you can sort of start to get these patch-to-patch fluctuations. Well, but you don't want it to be as steep. I mean, if you have it to be super steep below about minus 13 or so, you start to way overproduce the number of Milky Way satellites. So it's okay to integrate down to minus 13 or so with a steep luminosity function and then continue with a shallower one. This provides more photons, okay, but it doesn't really overproduce the number of galaxies around. So I think this is probably the answer there. You just want to get, that's why you can go all the way down to minus 3. You just have a much shallower slope that doesn't overproduce. I think that's the exact tension you have to sort of walk the line. I think that that's certainly true, but the problem is nobody's really come up with these kind of processes and why they're only operating in globular clusters today. So I think, you know, there's lots of interesting models, and I think that's absolutely right. So I 100% agree with that. But I think we need to understand, why is that only operating then? Is it something that's really only for, say, 2 to 4 solar mass stars or 2 to 8 solar mass stars, something interesting only in the reionization era? Why is that? I mean, you can sort of see that young clusters, younger than 2 gigayears, don't have multiple populations, but older than 2 gigayears do. So there's a lot of interesting constraints, but I don't think there's any model that really fits here. So I agree you don't need these, but a lot of the models that do it with AGB stars, fast rotating massive stars, anything like that, you do need this kind of Yeah, so I haven't actually done that. This is work in progress, and there hasn't been much progress, probably because I haven't done much work. But I think that's kind of a logical thing to look at. The part of the issue is, if you make this globular cluster formation epoch, you know, a gigayear or half a gigayear or whatever, it's really only for a gigayear or even a little bit less that you actually really have a very steep faint end all the way down, very, very faint, okay? And so I think but that is definitely something I'd like to look at there. Yes.
I'm looking at
Yeah.
some of these. I'm actually kind of looking at my paper prep. So.
Oh no, competition.
Well, no,
That's
it's
good.
not competition.
That's right, because I don't know anything about observations. I was pleased that I could pronounce magnitude correctly. Am I doing that right? Is that how it works? Yeah.
I guess.
You're not an observer. Was it just at least an order of magnitude more simple. Unless everything goes very smooth. Yeah.
Great, thank you.
Okay. So I guess we could. I don't know. Maybe there's too big a discussion now.